welcome you all to my channel. Let's begin today's class. You know that in organic chemistry, we study a reaction called as Haloform reaction. I won't talk much into the mechanism of this one, as the target of this video is something different. What do you know in Haloform reaction? That if you have an aldehyde or a ketone in such a way that it has a keto-methyl group, and if you give a strong basic medium or alkaline medium and you give halogen, mostly we use bromine, chlorine or iodine, because fluorine cannot be used due to its high electronegativity and the other factors. So it will give you a carboxylate ion, and the most importantly there will be a precipitate of this which is called as haloform. We do have a mechanism for this and we do have many aspects over here. And let me tell you that not only this aldehyde or ketone which is having a keto-methyl group, even alcohols can undergo this reaction if the alcohol is having CH3 CHOH group. In maybe some other video I will discuss about the mechanism and detail of this. But the target of this video is something different. Suppose if you are having, so this group is keto-methyl group, and the presence of this is very important if you want the success of this reaction. But suppose you are having this compound. I haven't talked about the alkyl group. Look at this. I haven't talked about the alkyl group. I do not know which alkyl group is there. But my question is, will this undergo haloform reaction? That is the question. That means in the last introduction, I told you that whatever is having the keto-methyl group in case of aldehyde and ketone, or if it is in the alcohol, then whatever alcohol you select, you should have CH3 CHOH group, which actually ultimately convert into CH3 CO group. So nothing like that is visible here. But still, will it manage to undergo haloform reaction? Let us see that. First of all, what kind of compound we can call this? It's a diketone compound with active methylene group. It is a diketone compound with active methylene group. This is your methylene group. When this is present in between two CO groups, it will be called as active methylene group. Mostly we select these two CO groups surrounding this CH2 group. Now this CH2 is active. This is because if this is losing one H plus and this is getting a minus charge, so this carbon ion is quite stable, because you can understand that it can undergo resonance from both the sides. So as this is quite stable, therefore the release of H plus from here becomes very easy. So this becomes an active group, and that's why we do call it as active methylene group. So first of all, I have introduced that what is an active methylene group and how do you select an active methylene group. Now the point is, these two hydrogens that are present with this CH2 group in between these two CO groups, they are replaceable, because once you replace that H plus, whatever carbon ion you get, that is well stabilized. So let us start with this. So suppose if I am having this RCO CH2 COR. What I told you that time, that you do not have any idea about which R group you are talking about. So if I give it OH minus, so this will take this H plus, okay, and that will release water. I'm not writing that. So it will give you RCO CH minus COR. You can definitely show the resonating structures by sight. But now if it reacts with an iodine, so what will happen? Due to the repulsion of this negative charge, these electrons which could have done a homolytic cleavage will now undergo heterolytic cleavage, and this will get a del plus and this will get a del minus, and this will be there to attack this minus charge, or vice versa. So what are you getting? It is giving you RCO CH, I can write it here, ICOR. You still have a hydrogen atom which is acidic. So you again give it OH minus. The OH minus will take this H plus, and that will again come out in the form of water. So this will give you RCO CI minus COR. You must be knowing that this is even more stable than the earlier one, because there now you are having one iodine atom which will also create the minus I effect to some extent. So this is quite good. In a similar manner like the earlier case, now it is having a del plus, it is a del minus, so the del plus will again go and attack over here. So you are getting RCO Ci2COR. So we have first understood that we are actually removing these two acidic hydrogens of the active methylene group, so that, I'm sorry, there will be a Ci2, so active methylene group, so that we can actually substitute these two hydrogens by the iodine atoms. Is it clear so far? Now understand. Let me just check whether the frame is okay. Fine. So now if I start with this, if you want to copy, just copy this. And now suppose if you are having RCO Ci2COR, let's move on with this. Ask yourself, is there any more hydrogen here which can be substituted? Hopefully no. So what will happen here? The OH minus, that will attack the OH minus, or let us just move it in a single arrow. So this will attack here. So what will it give you? RCO Ci2CO minus OHR. So actually what is happening here, this carbon, due to this opening of the bond opening, it is getting a plus charge, so it's becoming electrophilic, and OH minus is going to satisfy that. So this OH minus is coming to attack C, and this OH is getting attached with the carbon. So what will happen now? This O minus has to come back, because you have done a very wrong job. You have just opened the bond between the carbon and oxygen, and the double bond should not be open. This is thermodynamically unstable. You have supplied energy, so you have to regain that. So therefore this will come back. So what will happen? This group will come out. So it will give you RCO Ci2 minus plus RCOOH. So you are getting a carboxylic acid here. Now this is a mild base, because this minus charge can also make a resonance here, and there are two iodine groups, but still it is a base. It will work as a base. So this will go and take this H plus. So I can say it is a proton transfer. Making sense? So it is what? It is a proton transfer. So you are getting RCO CHI2. So you are getting one more hydrogen from here. After that, you can again treat it with OH minus. Hopefully you can do, because this hydrogen now with that carbon which is beside one CO group. So CO group again creates a bond movement. This is minus, this is plus, and that will make this hydrogen acidic. So removal of water will take place, and we will get RCO Ci2 minus. You obviously can understand now that this is now again going to attack with this iodine, and this is going to give you RCO Ci3. Think about that. We are already getting something which we want. Now again this will be attacked by this OH minus. This is becoming electrophilic due to the same bond opening. In the Pauling scale, oxygen is having the electronegativity which is equals to 3.5 and carbon is equals to 2.5. So oxygen is quite more electronegative than carbon. So OH minus will go and attack here. So RCOH O minus Ci3. It will again come back, and definitely, except this, there is no other living group here. No other good living group is here which can leave this compound or this species and can give you something. So the only option is Ci3 minus. So Ci3 minus will come out from this and it will give you RCOOH. This minus charge again will take this H plus, understandable. This is again a mild base. For example, if there will be chlorine, it will be even less basic, because chlorine is having much more minus I effect than iodine. So that one will give you again a proton transfer is taking place here. We are writing it as a proton transfer, and that will give you CHI3 plus RCOO minus. So think about it. So the compound diketone, which is having an active methylene group, is going to give you the positive iodoform test, even though we are not bothered what these R groups are. So any diketone, if it satisfies all these conditions, it will undergo haloform reaction. Make sure you understand this. You have the video open for you 24 hours. You just go through this again and again. Practice it well, you will be able to understand. Now, this was a concept where we cannot see. Please understand. This video is, that's why important. I have shown the two bifurcation of haloform reaction. The first one, where we cannot see a keto-methyl group directly. We don't mind if it is CH3 here. Okay, that is not a fact, because the CHI3 in this time is coming from something else. Generally, if it is COCH3, normally if I am talking about, so this CH3 group is actually converted into CHI3, but here it is not. Even if the CH3 groups will be in these two R groups, so they will be intact till end, and whatever iodoform, haloform, anything we will be getting, that will be from this area. Making sense? So this was a case where we cannot see a keto-methyl group, and we are having the idea that it will undergo haloform reaction. Now something else, something different, something reverse actually. Now we will see that there is a compound which is having a keto-methyl group. But the question is, will it undergo haloform reaction? Let's see that. So we have a compound called ethyl acetoacetate. Okay, so what is the formula of this? CH3CO CH2COOH. I think for the last example, you have even got the concept how the mechanism of haloform reaction is taking place. Okay, so this is CH3CO CH2COOH. It is the ethyl acetoacetate. Think about it. So where is the acidic hydrogen here? Ask yourself, where is the more acidic hydrogen here? Obviously at this CH2 position. Where is the more acidic group here? As obviously at this position. Okay, so let us start with this. So CH3CO CH2COOH will be attacked by the OH minus, same as earlier case. So I'm doing little fast. So this will give you CH3CO CH minus COOH. After that, you can give it iodine. So that will give you CH3CO CHI COOH. Fine, fair enough. You again give it OH minus. So it is CH3CO C minus I COOH. We are proceeding like the earlier case. Okay, I hope that is understandable. So again, if you give it like this, so this will give you CH3CO Ci2 COOH. So I hope you don't mind if we have done this little fast. So this is the product that we are having now. Please have a look on this and please copy this, because I will keep this compound over here. So you are having CH3CO Ci2 COOH. Making sense? Now there is a question at this moment. So at first you always must understand that when the base attacked, it always select the methylene group, because that is more acidic. Okay, you don't have any other option. So I write this again here. So CH3CO Ci2 COOH. Now please look. So like the earlier case, this bond will open and this OH minus will attack over here. You can ask me, why not here? This could also undergo the same attack by the OH minus. Now let me tell you, if this opens, so this carbon gets a plus charge, this gets a minus charge, automatically at that moment this one will exert the plus R effect and will diminish the plus charge on this carbon. That's the problem. That's why this OH minus selects to attack over here and not here. Number one reason. Number two, steric hindrance is also a effect here, because this OET group is comparatively larger group. As a whole, it is a larger group than this one, CH3. So I can say that this is less sterically hindered, but the first point, first example, first reason rather is most valid reason, is more valid reason. Okay? So in this particular case, this OH minus is going to attack on this carbon, which is delivering OH, Ci2, COOET. Making sense? Fine. It will come back. This is leaving group, good leaving group rather. So that will give you CH3 COOH plus Ci2 minus COOET. This minus charge will come and take this H plus out. So proton transfer. What are you getting here? We are getting here CH3 COO minus plus CHI2 COOET. Clear everybody? So we are getting CHI2. So this hydrogen has just transferred. This hydrogen has just transferred from here. Okay. So what we are supposed to do now? This hydrogen has just transferred. So what we are supposed to do now? This time we are having this CHI2 COOET. This is comparatively acidic. So as the earlier case, we will remove this H plus, which will generate Ci2 minus COOET, which will then be attacked by the iodine, and that will give me Ci3 COOET. Oh my god, we are done. Yes, we can see a Ci3. Whenever we can see a Ci3, we mean we are there, we are completing the haloform reaction. Let's see what happens this time. Once you have done that and you are waiting that yes, your job is almost done, you are there, it's a kind of eureka feeling, see what happens. This OH minus, so this will now attack here, because this is having, there's no more hydrogen from anywhere which it can abstract. So the OH minus will go and attack on this carbon, which will give you this one. Making sense, everybody? Here comes the most important thing. When this will come back, this should come out? No. This is a better leaving group than this. Here is the problem that is happening. ETO minus will be a better leaving group than Ci3 minus. Think why? Write down in the comment box. So it will give you Ci3 COOH plus ETO minus. So what is that? Triiodoacetic acid. Triiodo, think about it, it is CH3 COOH, where the 3 hydrogen atoms have been substituted by the iodine atom. So Ci3 COOH, triiodoiodic acid, it is now working as a base, will take this H plus, will give you ETOH plus Ci3 COO minus. So where is my haloform? Alas, we haven't got it. So this is a very important concept. I would like you people to participate and to comment that why this one will leave. I told you that it's a better leaving group, but you have to justify why it's a better leaving group. And there is the catch of the whole reaction. Hopefully you will do that. You will watch this video peacefully with all understanding points to be cleared, you write it down again and again. You make sure that you definitely go through the whole concept multiple number of times in loop, and then try to get how this is happening. And this one is a very simple concept, why ETO minus is living here instead of Ci3 minus. If Ci3 minus would have come out, yes, we could have got the Haloform reaction again, but we are not being able to do that. Okay, so please do watch this video. If you like, do share, like and comment. Comment is definitely necessary because that will also help me to interact with you and to clarify your doubts. Thank you. Stay well.